Hello, ladies and gents. We're going to talk about how heat transfers from one place to another. And there are three primary ways that heat can flow. They're called conduction, convection, and radiation. And in this video, we are going to talk about conduction. In subsequent videos, we're going to talk about convection and radiation. So let's define conduction. Conduction has buried in that word contact, or you're touching something. So thermal conduction is actually defined as a transfer of heat by collisions of particles, often electrons, within a substance. It's a transfer of heat by touching. This is what happened when you were a wee little kid and you would reach for something hot, and your people who loved you would say, "No, hot, no." They're trying to protect you from heat transfer via conduction. If you would take a piece of metal and put it in some sort of a flame, the molecules in the flame would get increased kinetic energy. And as those molecules bumped into other molecules next to them, via conduction, the heat would be transferred from where the heat source is down the metal, which is a good conductor, to your hand. That is a classic example of heat transfer via conduction. Now, metals are good heat conductors. They have very, very low specific heat. And one of the primary reasons they have low specific heat and are such good heat conductors is because they have free electrons. If you remember from chemistry, most metals have 1, 2, or 3 outer or valence electrons that are free to move. And in a metallic bond, there's kind of a soup of free electrons that sort of surround these metal atoms. And if heat is added to one side of a substance, this will cause these individual molecules to vibrate more violently. They are free to move. They can knock into their brethren. And that transfer of kinetic energy, particle to particle, one object hitting another, will travel all the way through that piece of metal. If you have something that is non-metallic, if you remember from chemistry class, these are not good conductors. These are good thermal insulators. And it goes back to the chemistry. In a non-metallic things, they tend to favor an awful lot of covalent bonds. And so these things tend to share electrons. They are locked in some sort of a crystalline structure. There are not free electrons that are free to zip along from one place to another. And it just slows down the whole process of thermal conduction. Now, this is the thermal conductivity equation, and we will have a couple homework problems and potential test questions with this. Here's the equation itself. Delta Q over delta T, which is the change in energy per change in time, is defined as the speed or the rate at which heat energy flows. Now, this is how much energy in joules passes a point per second. And a joule per second is a watt. So this is interesting because it actually is solved for two things, not just one. But sometimes you'll see this equation written also equal to capital P for power, and power is written in watts. K is something called the thermal conductivity constant. That's going to vary depending upon the material you are working with. A is the surface area of the material. Delta T is the change in temperature from one end of something to the other that the heat is conducting through. And L is the thickness of the material in meters. Before we do some math with this, I want to look at this thermal conductivity equation and talk about what this equation actually means. So first off, it says that the rate of heat flow, delta Q over T, depends upon A, directly proportional to surface area. Well, you woke up this morning understanding this, but you didn't maybe know that there was an equation that went with it. The classic example is, what do you do, or puppies or kitties or small children do if they're cold? Yeah, we curl up into a tight little ball. People have a tendency to wrap their arms around themselves when they're cold. Little kids sleep all bundled up in a little tight ball when they're cold. And it's an thing instinctively that we understand that if we reduce our surface area, we are going to stay warmer. It is going to reduce our heat loss, the rate at which heat flows away from us, by reducing our surface area. Now, on the flip side, if we happen to be very, very warm, we just spread out all over the place. Little kids do it, dogs do it, people do it, and we increase that surface area, and we are going to increase the rate at heat flow, and we're going to be cooler in the long run. Another classic example of this are animals in polar regions versus animals in equatorial regions. If you look at penguins, penguins evolved to live in the very northern or very southern climates. And penguins are really little footballs with little feet, very low surface area, little walking balls of butter. And that tight, compact form means they have a low surface area and a small quantity of heat loss. Something like a giraffe that has long limbs, long neck, long skinny tail. All of these things are designed to dissipate heat because giraffes evolved in a hot equatorial sort of parts of our planet. You can also see this in building design. This is a collection of buildings that were designed to be, these are modular structures used in the Antarctic for laboratories and building structures. The reason they are on feet like this is as the snow falls, they can actually hydraulically lift these higher and higher and keep them level and above the snow. But notice how compact each one of these little structures is. Not a lot of extraneous shapes and doodads, because the smaller, more compact they can make it, they can keep the heat in more completely. Old-fashioned Victorian homes built 150 years ago, heat was cheap. Everybody burned wood. Wood was everywhere, trees were everywhere, and labor was cheap. And so having a building that had lots of cupolas and lots of turrets and all sorts of weird doodads that hung out, it was great because it was pretty, but it's very, very expensive to heat because this is a high surface area structure. So it's going to lose heat much more quickly. The conductivity equation also says that the rate at which heat passes through something depends on the thickness of the material. You know this if you have ever insulated a building or paid for insulation to go into your home, etc. The thicker the insulation, the better that R value, the slower the rate of heat loss, and the more the heat is going to stay in. It also has to do with things like a cast iron pot and aluminum pan. This cast iron pot is much thicker, and because it's much thicker, heat is going to be maintained. It's going to take a lot longer to heat it up, but it's going to cool down much more slowly. If you've ever cooked anything in a little aluminum pie pan, it heats up quick, but boy, howdy, does it cool down quick. It's not useful to keep something warm. And then this poor fellow wandering around on a snowy day in his shorts, yeah, I don't know even what to say about that, but less clothing, he's going to be cold, I think. The rate of heat flow also depends on something called this thermal conductivity coefficient. This is how we quantify how well things do at conducting heat. So let's take a look at the cast iron pot and the aluminum pie pan. Now the cast iron pot, let's see, iron, here we go, steel and iron, has a thermal conductivity of about 80. Now 80 versus aluminum of 220. This is about 3 times faster than the cast iron. That means that heat is going to go through the aluminum pie pan about 3 times faster. It's going to heat up 3 times faster. It's also going to cool down 3 times faster. If we take a look at fatty tissue has a thermal conductivity constant of about 0.2. That's very, very low. Why do I mention that? Well, I don't know about you, but in the winter I tend to put on a little extra weight. And if you look at animals that are designed to live in the Arctic, they evolved to live in that Arctic, they are also evolved to have more fatty tissue because that is natural born insulation. With a low conductivity constant, keep that heat in. Meerkats, very, very similar in size than penguins, but they are long, skinny, lean creatures without very much body fat. They're an equatorial African animal, so they don't need to keep that heat in. They have to worry about regulating their body temperatures and not overheating. One of the other things that the rate of heat flow depends upon is the change in temperature. This is referred to as the temperature gradient. What is the difference between the inside and the outside temperature? What's the difference if you stick a poker in the fire between this end of the poker and that end of the poker? I don't know about you, but I live in the North Country, and what I've discovered is when it's about minus 20 degrees outside, my heating bills get really, really big. Now, we keep our house pretty consistently at about 68 degrees Fahrenheit, but my heating bills get nutty crazy big when it's really, really cold out, when the thermostat goes way down. And that's because of this temperature gradient. The colder it is outside, the faster the heat is going to flow through my walls and through my insulation. When the temperature outside is only 50, well, you know what? And I'm trying to keep it at 68, the rate at heat flow is going to be much, much less, and my heating bills are going to be much, much less. Here's a question about that temperature gradient to see if you kind of grasp the idea. So let's say a person goes to a restaurant and they order coffee with their meal, and they don't plan on drinking the coffee until the end of the meal, but the server brings it at the beginning. And you want to keep your coffee as warm as possible, and you like cream. So here's the question. If you want to keep your coffee the hottest at the end of the meal, should you add the cream right away, or should you wait and at the end of the meal add the cream right before you drink it? What do you think is going to happen based on this rate of heat loss is dependent upon the temperature gradient? Now, believe it or not, I have had dozens of students through the years who have actually done this. They've gone to a fast food restaurant, they've gotten 2 identical cups of coffee, and they have taken a thermometer with them, and they have done this experiment. And every single time, this one is hotter at the end than this one. And the reason why is if you make the change in temperature smaller, the rate of heat flow goes down. If you keep the change in temperature large, let this hot black cup of coffee stay really, really hot, the rate of heat flow gets nutty crazy fast, and it will actually be colder out the other end. One of the questions I've been asked hundreds of times through the years of teaching physics is this: which freezes faster, hot or cold water, if you're trying to make ice cubes? And I am going to challenge you to try this for yourself. I personally have done this half a dozen times in my own home. Mostly it's because somebody wanders into my house, we start talking about it, and I go, fine, let's try it. And we do a little experiment. So if you're going to try this, I'm going to ask you to be very scientific. So how do you be scientific about this? Only change one variable at a time. So here's some things I'm going to ask you to think about. What are you going to use for freezing the ice cubes? Are you going to use your freezer, or are you going to use the big outside in the winter time? Because in a freezer, if you put in hot water, does that mean that the freezer, the machine, is going to have to operate faster or harder or with more wattage in order to freeze that hot water? How are you going to define hot or cold? Are you going to use hottest hot water in your tap, coldest cold water in your tap, or are you going to actually boil the water right before you put it in? One of the challenges, if you want to be this nerdy, is mass the ice in the water before you put it in the freezer and then after. Question: do you lose any mass to the environment into the freezer, and will that have an effect? How do you define frozen? A lot of students get impatient when they've done this, and when there's a tiny little skim of ice on the top, they call it frozen. Or are you going to wait for it to freeze all the way through? The surface area of the container, are you going to use a classic old-fashioned ice cube tray? I've had a lot of people use little plastic dishes or cereal bowls or Cool Whip containers. And what if you do use boiling water? What about that heat of vaporization? What's that going to happen? Or how's that going to affect things? And then that temperature gradient, is that an effect? I'll tell you right now, I have done this myself, and every time I've done it, I've gotten exactly the same results. But through the years, about 20% of my students get the opposite results that I get. And I know why, because they all do the same thing. But I'm not going to tell you what happens. I want you to try that for yourself and let me know what happens. All right, we will see you next time, and we're going to talk about a different method of heat transfer.